Okay, right, so just gonna... On Friday, we finished off all of our work on hidden surface removal. So that stuff we did about the FP trees, that was the last topic on hidden surface removal. Now we're going to be looking at a different topic. Broadly speaking, it's called rasterization. I'll explain all what these words mean, and you're going to be hearing quite a few terms. And the particular thing we're going to be looking at today is DDA algorithms. Now, I have produced a set of notes for rasterization. They haven't yet arrived from reprographics, so they should be. I was expecting them this morning, so they'll probably arrive later today. So for this lecture, you won't have any notes, but they are coming, and they'll also be on Moodle as well. So I'm afraid there's no notes for you for this lecture, so I should have your full attention. Okay, so as I mentioned, we're going to be looking at DDA algorithm today. Well, we're actually going to be looking at two, but the first one we never use. But I'm just going to explain it because it's a nice introduction into what we're doing. Okay, so we're going to be looking now at rasterization. Essentially, what you have is on a computer screen, how graphics and how displays work is you have an array of lots and lots of little squares, and these squares are called pixels. So if you've got your mobile phone or a monitor, you're probably aware of that. On this slide, on the right, up here, okay, this is what we call an idealized image. So let's say this is a picture that I want to display on our computer screen. So idealized image. Obviously, this projector is using pixels, so what you're actually seeing it is a rasterization, but pretend it's an idealized image. Okay, so that's what you want to display. That's what you want to show. Unfortunately, we have to approximate it using pixels. So beneath that, you can see what we call a rasterized image. Now, a raster is simply the name given to the array of pixels. So if you have, when you're looking at a computer screen, you're actually looking at a raster. Okay, so yeah, so the raster array is the array of pixels. Rasterization is going from, okay, that's what we want to show. That's our approximation. So going from that to that is what we call rasterization. The top image, that's what we want to show is the idealized image. Okay, and as you can see, you'll never get 100% clear image. Obviously, this is quite a blocky example. Modern computer displays have got really small pixels. I think modern got something like 4,000 pixels across on the top end TVs and displays now. So they are almost imperceptible. But at the end of the day, we still have these squares to work with. So that's what we're going to be looking at over the next couple of weeks. Quick note about raster arrays. Okay, if you have NX pixels along the horizontal and NY pixels on the vertical, a raster array is NY by NX matrix. But there's also a third dimension. Now, so we're going to have to start visualizing or start thinking about three-dimensional arrays. It starts to get a little bit hairy. So we have this third dimension which has 3 in it. So we have NX and NY, those are our pixels. But each pixel, you have 3 numbers. Okay, so imagine a building, imagine a 3-story building with NX rooms in one direction and NY rooms in another, and you've got the 3 stories. So it's kind of like a 3D array. The reason why there are 3 numbers for each pixel is this is how we define the color. Now, the color of a pixel is defined using quantities of red, green, and blue. Red, green, and blue are the physical primary colors. So I think I asked this question a few lectures ago. Any artists in here? Nobody said anything. So if you remember if you ever mix paint, your primary colors are not red, green, blue. That's the one. Thank you. Yeah, you can see I'm not an artist. But we for physics, for light, primary colors are red, green, blue. We're going to be using Matlab, and Matlab's got a command called image that can be used to plot a raster array. Okay, so I'm going to go over to Matlab now. Hopefully it's open somewhere. Here we go. Right. What I want to do is go to, oh dear, I have to quickly change folders. Where's downloads? What I can do is I can sneakily open up one of these. We're not going to be using that yet. I just want to change the folder to it. Okay. Right. What I'm going to do now is in this folder, I have a photograph. So what I'm going to do is I'm going to load in the photograph. Okay, so this command in Matlab, load Cavendish. Cavendish is a JPEG. Okay, so it's just a photograph. And what it does, it loads it in. And if I go who's Cavendish, it's created a raster. Oh, that didn't work. Okay, this is why we have backups. I was hoping to show you this. Imread. Okay, I got it wrong. So if I go x equals imread Cavendish. Okay, there we go. It's loaded in an array, and if I go who's x, okay, you can see this array is 240 by 320 by 3. Okay, that means it's got 240 pixels in the y direction, so the vertical direction, 320 across, and sort of 3 deep. Okay, so remember when we're doing matrices, we always go row then column. So here we got 240 in the row, which is down the vertical side, 320 across, and 3 deep. Okay, so that's my raster array. So if I do image on X, and there we go. That's a picture of my cat. Okay, that's Cavendish. That's my cat Cavendish. Right. So if you sort of look closely, I've sort of enlarged it here. You can start to see the blockiness. So I took a photo. I actually had to reduce it because modern cameras now are too high res. So I reduced the photo and I've displayed the image. So each of these squares is defined using 3 colors: red, green, blue. You just mix those 3 colors. And so, for example, this I know this wooden bit here will be some quantity of red, green, blue. What I want you to notice is on the vertical axes, have a look at the scale. Okay, the scale is going ascending order, but down. Okay, this is because for raster arrays, the top left-hand corner is your origin. This is because engineers, when they build the computer displays, they put the origin in the top left-hand corner. So therefore, if you're ever doing anything with rasters, you have to do that, which is kind of annoying. What we're going to do when we have a look at the drawing stuff, we're going to flip so our origins at the bottom. So there's a command we can use, which I'll show you later, which means we flip it. So we assume that the bottom left is our origin. Okay, so that's Cavendish. Don't think she's cute. She's an absolute menace. I think I've got scratches on my hands to prove it. So that's plotting. That's the command we're going to use, that image, and then in the brackets, the raster. Okay, I mentioned we're using primary colors, red, green, blue. This is what we call an RGB color model. Now, there are a few color models out there. RGB is the one that Matlab uses, although you can actually switch to other sorts of color models, but this is the only one we're going to focus on. And RGB stands for red, green, blue. These are the primary colors. Now, if you have a look down in this bottom right-hand corner, this is what we call a color wheel. If I was to shine red light, green light, and blue light, not yet. If I was to shine red light, green light, excuse me, blue light on a surface, what would happen? Obviously, where you're shining the red light, it will appear red. Okay, green light will appear green. But where you mix in the colors, so if I was to get a red torch and a green torch and shine it on, we'd get yellow. So this is not like mixing paint. This is mixing light. So red combined with green gives us yellow. Red combined with blue gives us magenta. And blue combined with green gives us cyan. Okay, so we could combine red, green, and blue to create colors. Now, if we had 1-bit color, this is what we call 1-bit color. When I say 1-bit color, I mean each primary color is using 1 bit of memory. So either it's 0 or 1. So either we've got all of that color or none of that color. If we have, well, it's actually called 3-bit color, but we're using 1 bit for each color. We can produce these 8 colors. Okay, so different combinations. You can see here, this is essentially binary. So this is your 8 numbers. So 2 to the power 3 is 8. And we can produce these colors. If we shine all of the light, so if we add red, blue, and green, as you can see, this intersection in the middle bit is white. So combination of red, green, and blue light actually gives us white light. If we don't shine any color whatsoever, we've got black. So black and white is all of our color, black's none of our colors, and then we got the various other stuff. Around this color wheel, though, you can notice there are gray shadings. So we could have, let's say we could have sort of 1/4 of red and maybe all of green. Okay, that will give us more of a green shade of yellow. Okay, so we can have different levels. If we had 8 bits per each color, so in other words, we've got 24 bits. It's a possible number of 16,772,216 colors we produce. So that's just using 8 bits of memory for each primary color. Human eye has been estimated, it can at the most distinguish 10 million colors. So there's no point going above using 8 bits per each primary color because we won't be able to detect it. Our eyes are actually quite poor when it comes to detecting colors. Sorry? Yeah, I mean, it is quite difficult to test for. It's subjective. Like how do I know, right? How do I know? But this color I'm seeing is the same as the color you're seeing. There's no way of knowing. Also, we humans are quite poor at seeing blues. We're actually a lot better at seeing reds and yellows. Maybe it's danger. Maybe it's an evolutionary thing. I'm not sure. So it is kind of a bit subjective. Within computer graphics and computing and mathematics, we don't tend to go past 24-bit color because we assume there's no point. Okay, 24-bit color that came in mid-90s, known as true color. So we're saying, okay, that's our best possible, well, as good as possible as we can do it. Back in sort of early 90s, if anybody, you probably maybe not even born then, but played computer games back then, you had 8-bit color. Okay, 8-bit color used 3 bits of memory for red, 3 bits of memory for green, and only 2 bits of memory for blue. Okay, combine them, you had 256 different colors. Okay, so I think it's become a bit of a resurgence in gaming, like all these old school games. Okay, so that's RGB. Right. So what I've got for you now is I want you to pretend to be a computer. The problem we have is how do we represent an idealized image only using pixels? And this reminds me of when I was I remember doing this at primary school. So this is not, don't think I'm taking the mickey, but you can tell when our when my primary school teacher was either couldn't be bothered or hungover or something, because she used to give us squares of she used to give us blank squared paper and say, "All right, draw some patterns on that," and then couldn't be bothered to teach us. This is kind of similar. No, I'm perfectly fine. No, don't drink on a school night. Okay, what I want you to do now is we have a 10 by 10 raster array. There we go. Okay, 10 by 10 raster array. Let's say that's our screen. What I want to do is draw a line, represent a line on that screen. So what I want to do is draw a line between the pixels with coordinates of 1, 1 and 10, 7. So I've got a pixel there at 1, 1 and 10, 7. I've got a pixel there. Okay. Anybody got rulers on them? Excellent. You're going to have to share that around. I think you're the only one. Okay, draw a line between them. And I'm using crosses because I'm lazy. Not hungover, just lazy. Okay, and what I want you to do is just shade in the squares which are closest to that line. What you don't want, though, is to shade more than 2 squares for a given column of pixels. Okay, so you can see I've done it here. Notice if I look down a column of pixel, I've only got 1 pixel shaded. Across rows, there's a couple of times when I've got 2 pixels shaded across. Okay, so our straight line was the idealized image. We've rasterized that straight line. What problems have we got? Sorry? Whereabouts? Oh, right, yeah. So do you mean this one here? Yep. But I only wanted, this one was kind of like, I had a choice between these 2 pixels. To be honest, I could have done that one. It would have still looked okay. You did them all? Yeah. What you've done is an example of what we call Wu anti-aliasing, which we'll come on to in a couple of weeks. So, yeah. But if I wanted my line to be 1 pixel wide, that's what I had. The problem is we have here is it doesn't look like a line. It's kind of like jaggedy. Okay, that's not a smooth line. If I was to draw a horizontal line, it would look all right, wouldn't it? If I was to draw a vertical line, it would look okay. But with pixels, because pixels are squared, as we go up on a gradient, we've got like this jaggedy thing coming in. That's called aliasing. Now, in a few weeks' time, we'll be looking at methods to alleviate that. But for now, this is the problem we have. Okay, we want to be able to draw a line on our computer display. How did you determine where these pixels were? Well, I just looked at them and thought, which is the closest one? How does a computer do that? Okay, so remember, I keep saying computers don't have eyes. They don't have our reasoning. So we have to develop algorithms to actually determine where these pixels are. Okay, and that we're going to be looking at 3. We're going to be looking at 2 today and 1 on Friday. Okay, that was a quick activity to get you to do that. So this is the problem we have. Okay, let's give a start point and an end point of our line. I've called them A and B. So we've got coordinates of AX, AY down here, BX, BY up here, the straight line between them, and we want to shade, or what we call illuminate, the pixels, which is closest to that line. Okay, what we tend to use is delta X and delta Y quite a bit. Now, delta X is simply the distance, and on the X direction, between the end point and the start point, and delta Y similar to the Y direction. Okay, and this brings me on to pixel coordinates. Okay, so when we're dealing with pixels, we want to know where they are. Okay, so each pixel has coordinates, and I'm going to call them X and Y. Okay, I know we've used X and Y in the past for world space, but now we're sort of leaving behind all of that world space, screen space palaver, and we're going to rasters. Okay, so when I talk about X and Y, I mean these are my pixel coordinates. And these are the coordinates at the center of each pixel. So pixels are discrete quantities. You can't have half a pixel. It's either a whole pixel or nothing. Okay, so they're discrete quantities. So x and y are members of the natural number. Members of a set of natural numbers, and x is in the range 1 to nx. Okay, so we can't have x having a coordinate of 0 because that's not a natural number. We have to start at 1. And y is also 1 to ny. Now we have screen space coordinates which represent our idealized image. They're real numbers. Okay, and they're in the range after we've done all our clipping and stuff like that. They're in the range -1 to 1. So we need to convert from screen space coordinates xs and ys to raster coordinates x and y. And I think I showed you this when we looked at the z buffer. Okay, this is what we do. Essentially, we scale them. Okay, so we have some scale, scaling factor, and this is quite simply the number of pixels divided by either the width or height. So in other words, nx divided by 2, because our height and width of our screen space is 2. 1 minus -1 is 2. Okay, so if you have a scaling factor in the x direction, you take the number of pixels across, divide that by 2, and then you multiply that by xs plus 1. The reason why it's xs plus 1 is if xs was -1, plus and 1 gets to 0, times it by the scale, and then this max 1 or whatever that number is always assumes we're starting from the first coordinate in. So that's called scaling the coordinates, or converting from screen space to our raster. Okay, now we're going to look at driving axes. Essentially what this means is when we're looking at line drawing, which we're going to be doing the first few lectures, we increment along one direction at a time. So either x or y. So let's say we take x as the one we increment along. We illuminate one pixel, we step across to the right to the next pixel, and then see how far up we need to illuminate where the pixel is. Okay, so the axis used to increment the pixels by 1 is what we call the driving axis. Now this is whatever you choose it to be. You've got a choice between x or y, and you choose, it's up to you what which x or y you use for the driving axis. Bear in mind, that will affect the algorithms and the calculations which you have to do. I'm going to assume that x is the driving axis, unless otherwise stated. And we do have to sort of mess about with driving axes later. But for now, I'm just going to go across in the x direction and then calculate the height and the y. Okay, the first method we're going to be looking at is called the direct scan conversion. It's a rather flowery title, as are most things in this subject. Essentially, it uses a Cartesian equation of a line. Should be very familiar with you to use, sort of going back to GCSE level, y equals mx plus c. Okay, m is a gradient, so that's delta y over delta x. C is the point at which the line crosses the y-axis. Okay, if we insert these expressions for m and c into y equals mx plus c, we get this. Okay. Now, if x is our driving axis, x is easily calculated because we're just stepping across each time. We know what m is. M is delta y over delta x. So we've got a start and end point of a line. We can calculate what that gradient is. AY and AX are the x and y coordinates of the start of a line. Okay, so using that, we can build an algorithm. So this algorithm, what we want is, given a start point A and an end point B, I want to be able to draw or rasterize the line joining those 2 points on a raster array. Okay, so this is the first of the algorithm we're going to look at. Illumination color is just 3 values RGB. So pick what color you want, that's fine. Okay, so the algorithm using the Cartesian equation of a straight line, first thing we have to do is round a and b to nearest integers. And that's kind of done in this step. Okay. Oh, well, actually, it isn't. Actually, x and y could be non-integer quantities. So with rasters, we can only ever work with integer quantities. So the first thing we have to do is round our start and end points and nearest integers. We initialize x to be the starting point ax, and same for y. And then we calculate the gradient m. Now this while loop, what this does is this sort of fills in the whole line. Okay, so we keep doing these calculations until x, or while x is less than or equal to the end coordinate of x. So we start at a, we keep doing this until x is equal to bx. And what we do is we fill in the pixel at x round y. Now y could be a real number. It might not be an integer. That's why we have to round it. So we go raster x round y, and we fill in the color at that position. We add 1 to x. So that's essentially for the next time we go around, we've just stepped 1 pixel to the right. And we calculate what y is. Okay, so remember, this m is probably more likely than not to be a real number. Therefore, y will be a real number, hence why we have to round it there. Okay, so we keep sort of going through this loop, and we stop when we've reached the end of our line. A couple of things to notice: these sort of left arrows, all they mean is, okay, that value, that variable there takes on that value. We don't use equals in algorithms because it's not strictly equal in a mathematical sense. Okay, and we return, after we've done all that, we just return whatever our raster array is. Okay, when I first started teaching this, some students found following just the formal way of writing out an algorithm quite difficult to follow. So I started doing flowcharts. Now, this is exactly the same as the previous slide. It shows exactly the same information, but some people like it in a flowchart. It's more visual. Okay, so this does exactly the same thing. How familiar are you with flowcharts? Have you seen them before? Okay, so you have a start and an end of your method. Boxes are sort of doing things, so that's where you have to do things. This sort of rhombus shape is a decision node. Okay, so wherever you see this shape, it means, okay, you've got to make a decision. So here is x less than bx. If it is, we go down here. If it's not, we finish at end. This parallelogram means it's something to do with data, either input, output. Okay. So that's flowchart. Take it or leave it. Personally, I prefer this way because it's closer to sort of code, but some people who think in a different, more visual way prefer flow diagrams. I'll display them using both methods. Okay, that's the DSC output. One thing I do want to show you is if Matlab will work for me this time. I think I had this up earlier. Here we go. Okay, so what I've done is I've got some Matlab code. By the way, the notes has all this on, so don't worry too much about that. Okay, so I've written a function. I've called it DSC. That stands for direct scan conversion. It takes in an array which is ny by nx times by 3. Okay, A is the start coordinates, B is the end coordinates, and color is simply whatever color I want to draw the line in. Okay, so following the algorithm, we round coordinates A and B, initialize x to be ax, B to be by, and calculate m. There's your driving axis. I've actually used less than. It doesn't matter if it's less than or less than or equal to be honest. Okay, the only thing which may sort of cause some raised eyebrows is this line here. What you've noticed I've done is I've gone raster round y then x, not x and y. The reason being is how Matlab deals with matrices. Remember, we index a matrix, go row then column. So we go down, then across. So if I want x, y illuminated, I go y first, then x. So it's just conversion, just rather than Cartesian direction, x and y, we have matrix y, then x. Okay, add 1 to x for the next go round, and then calculate the next value of y. Okay, and if I just show you, yep. So what I've done here is just created a program, which hopefully when it runs, creates those lines. Okay, so this program, I created a raster array, 100 by 100 pixels. Color, so that was my color. 1 in the red, 0 green, 0 blue, so therefore I've got red lines. Okay, so that's initializing raster array. I initialized them all to be 1s because I wanted a white background. But if I had that to be 0s, actually let's do that. So do it to 0s, you get a black background. If I wanted a green background, I could have, no, let's not mess about. Oops. Okay. Right, and so all I did there, okay, draw some lines. I had a little for loop because I wanted to draw multiple lines. I've got 5 of them. Calculated some start and end points. And this is the most important thing. Okay, call in the DDA algorithm. So rasters was the output. It's inputted the raster array, start coordinate, end coordinate, color. And then I plot the raster, and then I do this. Okay, this is something which I had to Google to find out how to do it. Okay, set GCA y direction normal. This means when I, gone past it. If you look at the y axis there, it's assuming the directions in the normal direction rather than the top left being the origin. If you didn't have that, see what would happen. Okay, so you can see the y's are going down. Okay, just something to put in. Right. Okay, so as we can see, it gives us some lines. It works. It's rubbish. No one uses it. I've just shown you it just to sort of give you a nice introduction to it. One thing the actual algorithm we're going to be looking at is one called DDA algorithm, which improves on what we've just done. Okay, so moves on to the DDA algorithm, or digital differential analyzer. Again, one of these really flowery terms for something which is quite simple. Essentially, along a straight line, the gradient is constant. So where you are on the straight line has the same gradient. And so if it's constant, that means the y coordinate is incremented by the same amount every time we step to the right. Okay, so what we can do is we could rewrite the DSE algorithm by just adding a number onto y rather than having to calculate y. This cuts down on what we call the amount of floating point operations. This essentially means whenever a computer represents a number which isn't an integer, it's slower for the computer to do that. Now, these are very fundamental methods we're looking at. These are called millions of times per second. So the faster we can make them, the better. Okay, so essentially what the DDA algorithm does, okay, if we know that the pixel at xi, yi has been illuminated, the coordinates of the next pixel to be illuminated are simply we add 1 to x and we add m to y. Simple as that. So just 2 additions, and then we've got an improvement on the method. Okay, so very, very simple, very similar algorithm. The only changes here is instead of that complicated y, all you do is add n to it. Okay, very similar flow diagram. Again, when you get the printed notes, you'll see this, and you'll have more time to have a read of that. And gives us exactly the same output. Okay, I've noticed I've gone through it very quickly because not a lot to it, rather than you only have to change 1 line of code, but it's much faster, much faster. Okay. Right, so that was the DDA algorithm. Well, if you flip over your activity, one thing I want you to do now is use the DDA algorithm to draw that line. So this time, I don't want you just to draw a line and then shade the pixels closest. I want you to calculate the coordinates using the DDA algorithm.